These are the frequently asked questions for Algebra 2 for Section 8.3 Day 1. I'm going to start with number 13. Number 13 says, find the domain, points of discontinuity, and x and y intercepts of each rational function. Determine whether the discontinuities are removable or non-removable. So the first thing that we need to do is to go ahead and factor whatever we can. So we look at our numerator, 2x squared plus 5. And there is no common monomial factor that we can pull out of that. So that is as simplified as it's going to get. There is no factoring that we could possibly do. But in the denominator, the first thing we always check is that greatest common monomial factor, and that is an x in this case. So if we pull that out, again, that's like division. You take x squared divided by x, and you get x. And then you take a negative 2x divided by x and get negative 2. And a lot of people do just think of this backwards, you know, saying to themselves, if I pulled an x out of here, what would I have to multiply it by to get that back, to get that x squared minus 2x? But what we just found here was a good look at the domain and points of discontinuity. So our domain is going to be all reals except 0 and 2. And here's why. We are dividing in this problem. In fact, this whole chapter is about those reciprocal functions, so our division piece here. And if we put a 0 in our denominator, we will be dividing by 0. And if we put a 2 in our denominator, we will be dividing by 0. And those are undefined in mathematics. We cannot divide something into 0 parts. It makes absolutely no sense. So now we have our domain. Points of discontinuity, we just found them. Those are at x equals 0 and x equals 2. Then they want to know what the x and y intercepts are of each rational function. So start thinking, okay, x and y intercepts. If I want to find the x-intercept, that means my y has to come out to be 0. The only way that y is going to be 0 is if there is a 0 on the top of my fraction. So 0 would have to equal 2x squared plus 5. Well, let's see when that's going to happen. We would subtract 5 from both sides. Then we would go ahead and divide by 2. And at this point, when we take our square root, we realize, uh-oh, that's going to be imaginary. So we don't have any real x-intercept. Doesn't exist. Because again, when you take the square root of a negative, you're going to be working with imaginary numbers. So no x-intercept. Let's check out y-intercept. Y-intercept is what you get when your x is 0, because graphically that's where your graph crosses the y-axis. So if we go back to the original and we put a 0 in for x, we're really just saying, what do we get? Well, 2 times 0 squared is 0. 0 plus 5 is 5. But on the bottom, if we put a 0 in, we're dividing by 0. So that doesn't work either. That's undefined. Remember, that was one of our restrictions for our domain, is that we cannot put 0 in for x. So then it says determine whether the discontinuities are removable or non-removable. They are only removable if they would cancel out. And we see right here, there is no way for us to cancel either of those out. So these are non-removable discontinuities. So that really takes you through all the steps of going through it and finding everything that would be important about this graph that we would want to know before we started doing any graphing at all. Now let's look at 16. 16, right away I notice in my numerator I could pull a 3 out, and that would leave me with 2 minus x. And then the denominator is a trinomial, and it's not a special one. There's no common monomial factor I can pull out, first of all, but then I notice the 6 in the back, so this is not a perfect square or anything like that. And I'm looking for two numbers that multiply to positive 6 and add to negative 5, and that's going to be negative 2 and negative 3. Now, notice the similarity in the numerator with the 2 minus x and the x minus 2 in the denominator. And how you get that to reverse is by pulling out a negative. So notice if we make that negative 3 and now we multiply that back together, that will be negative 3x plus 6. And that's exactly what we had up at the top there for our numerator, just backwards. So it's equivalent is what's going on. And then we'll have an x minus 2 and an x minus 3. And you can see why they did that. They were trying to make us miss a removable point of discontinuity. So our domain, we do have some numbers that we cannot use in our denominator, and those numbers would be 2 and 3. So it will be all reals except for 2 and 3. And then they wanted to know about our points of discontinuity. From now on, I'm just going to put PODs for those. Points of discontinuity are x equals 2 and x equals 3. X and y intercepts. Well, again, if we have an x-intercept, that will occur when y is 0. So what we have to do is just try to get the numerator to be 0. And you could go back up to the beginning one if you wanted to. It might make your math a little bit easier. So we want to know, when does 6 minus 3x equal 0? We'd subtract 6 from both sides. And then we would go ahead and divide by negative 3. And x would equal 2. Problem? We can't put 2 into this function. Remember, look at our domain up there. We're saying x can't be 2 because that will make us divide by 0. So once again, we have an x-intercept where we have to put, we don't have one. It's none. Our y-intercept. Our y-intercept occurs when we have 0 for x. So let's go back up to the original and put a 0 in and see what happens. If we put a 0 in our numerator, 6 minus 3 times 0 is 6. And if we put a 0 in our denominator, 0 minus 0 plus 6 is 6. So we actually get 1 this time, and that will be a 1. So we have a y-intercept of 0, 1. And then we are supposed to determine whether the discontinuities are removable or non-removable. Well, what that means is, could we cancel them out? And as we look at that factored form here, we realize that x minus 2, that would be removable. So x equals 2 is removable, but we cannot cancel out that x minus 3. So x equals 3 is non-removable. So again, a lot to know about the graph before we even try to graph any of it. Then, find the vertical asymptotes and holes for the graph of each rational function. And looking at number 20, kind of interesting that the graphing is already done for us there. So what we want to do is determine if we have removable or non-removable points of discontinuity. So we see right away our denominator that we have an x equals 2 and an x equals negative 1 that would be problems. So far those are asymptotes. Now we have to determine if they're going to cancel out. If they're going to cancel out, then they're just going to be holes in the graph. So we do see here that x minus 2 will cancel from the top and the bottom. So that means that is no longer an asymptote. This is now a hole in the graph. But our x plus 1, that's not going to cancel, so that is a vertical asymptote. So VA, x equals negative 1, hole at x equals 2. So again, it's truly, is it removable? Can you factor it out and cancel it from the top and the bottom, in which case then it's a hole. But if it doesn't, then it's a vertical asymptote. So with number 21, we're going to have to factor our denominator first, and that of course is the difference of two squares, so x plus 2 times x minus 2. And in this case, we see that the x plus 2's would cancel out. So again, we'd start by, with our domain, noticing that x equals negative 2 would have us dividing by 0, which is not acceptable. We assume that it's going to be an asymptote until we see it's going to cancel out. So that's going to make this a hole in the graph. So points of discontinuity being holes versus being asymptotes. Now I think I have to go quite a few pages back here in order to get to the end of this assignment. There we go. Number 50 says, what is the x-coordinate of the whole in the graph of y equals, and then we have x squared minus 9. Well, I'm going to go ahead and factor that as the difference of two squares right away. And then in my denominator, I have 2x squared minus x minus 15. Now, just using a little bit of logic here. We're looking at what's going on and thinking, okay, it would have to have a 1 and a 2 in the front, 2 and the 1 in the back. And then in order to get negative 15, we do have different numbers we could choose from. However, educated guess would be that we're going to use the plus 3 or the minus 3 because they want us to see things that will cancel out. So I started thinking about the fact that it's probably going to be either negative 3 and positive 5 or positive 3 and negative 5. And then looking at outside times inside until I can manage to get a 1, a negative 1 in the middle. So looking at these numbers, we think, hey, you know what, negative 6 plus 5, that would be really great. And that would work right here because we'd have 5 times 1, which is 5, and then negative 3 times 2, which is negative 6. So this is first, last, and last, making this first, last, and last. And we do see that that x minus 3 would cancel out. So it says, what is the x-coordinate of the whole in the graph? That's going to be x equals 3. It did not ask for the asymptote, but we could certainly find that down there at the bottom by just setting 2x plus 5 equal to 0, and x would equal negative 5 halves for our asymptote as we go through there. Number 52 says, what is the y-coordinate of the vertex of this parabola? Well, it doesn't take you long to get that if you remember the form. And that is y equals a times the quantity x minus a squared plus k. So the vertex is going to be at 4, 5, and they just wanted the y-coordinate, so that's going to be 5. Good old h and k. Then number 60 says, sketch the asymptotes in the graph of each equation and identify the domain and range. So y equals a over x minus h plus k. So x equals 1 is our vertical asymptote for this graph. So let me get that on there. Again, dashed or dotted, not solid, that is a helper line. And then y equals 2, y equals k is our horizontal asymptote. All right, and now it's time to get a few numbers in here. And we realize that since our x value is 1, we probably want to put 0 and negative 1 to see what's going on the left-hand side of our asymptote, and then put in 2 and 3 to be on the right-hand side of the asymptote, and still see how close this will approach the center of the graph here. So we put a 0 into this bugger, and let's see what we get. 0 minus 1 is negative 1. Negative 2 divided by negative 1 is going to be 2, and 2 plus 2 is 4. Then we put a negative 1 in here. Negative 1 minus 1 is negative 2. Negative 2 divided by negative 2 is 1, and 1 plus 2 is 3. Then we go after our 2 and our 3, so put a 2 in. 2 minus 1 is 1. Negative 2 divided by 1 is negative 2, plus 2 is 0. Put a 3 in. 3 minus 1 is 2. Negative 2 divided by 2 is negative 1. Negative 1 plus 2 is 1. And away we go. So 0, 4 and negative 1, 3. And again, that does give us a really nice look at what's going on at the corner there at our new asymptotes, where we have this new kind of center of this hyperbola. And then 2, 0. And 3, 1. And there it is. Then it said, sketch the asymptotes in the graph of each equation, and then they want us to identify the domain and the range. So domain, we know we can't use x as 1, so it'll be all reals except x being 1. And then our range, all reals except for, again, our asymptote, 2. So y can't be 2. It can be everything else, just can't be those two things. All other real numbers are going to be fine. And let's see, there were a couple more. So 63 says find the inverse. There are two basic steps to finding any inverse, and that is switch x and y and then solve for y. So in 63 we would make it x equals 2y squared. We would switch, I've switched the x and y, now I need to solve for y. So we divide by 2, or write it as 1/2 x. You can write it x over 2 or 1/2 x, whatever you want to do there. But then we have to take the square root, and that's going to give us a little plus or minus business going on here. So plus or minus the square root of 1/2 x equals y. Now, we have a problem because there's a square root of 2 in the denominator, and we would want to get all of that fixed. Unfortunately, the book stops right there. We know we're not supposed to. We're not supposed to leave a radical in the denominator. So we would have the square root of 1 over the square root of 2, and then we have our square root of x. But what we're worried about is the numbers. So obviously that's going to be 1 over the square root of 2, and we would multiply by the square root of 2 on the top and the bottom and get the square root of 2 over 2. So this will be plus or minus square root of 2 over 2 square roots of x, which would just be plus or minus the square root of 2x over 2. That's really how far we should take it. The book basically stopped up here and said y equals plus or minus the square root of x over 2. But we should rationalize that denominator on that one. So switch the x and y and solve for y. Then number 76, 75, and 76, factoring each expression, just to make sure that everybody remembers what they're doing with factoring. And in 75, the first thing I'm looking for is, can I factor out a common monomial? Because I sure would like that 5 out of there, but can't do it. So in the front, I need the combinations of numbers that multiply to 5. Good news, there's only 2 sets. And then in the back, would multiply to a positive 1 and add to a positive. Well, that's 1 and 1. So not going to take us long to figure out this one. And either set there is going to give it to us. So then we do first and first, last and last. And there it is. And again, you could always do FOIL on it and double check that that's going to get you back to the original. Doesn't matter if you have the quantity 5x plus 1 first and then the quantity x plus 1 second. It makes no difference in this case because with either direction we would get this to work out to 5x squared plus 6x plus 1. Number 76 is 10x squared minus 10. And the first thing I saw was, hey, we've got an abundance of 10s in this problem, so let's take those out of there. Again, that common monomial factor has to come out first. Then I notice I have a difference of 2 squares, so that will be x plus 1 times x minus 1. So give the other two that are up there a try and see what you can do with this.